In this video, we will attempt an interesting astronomy experiment. During a convenient time of year, we face due south when the Sun reaches its upper culmination, also called a transit, on the local meridian. Here, we see the Sun during such a moment somewhere in August from a northern latitude. The yellow line marks the ecliptic, the daily path of the Sun. Local transit of the Sun is reached during noon, so no stars are normally visible. This video shows them in order to make a point later on. We notice that the Sun is nearly superimposed on the star called Regulus in the constellation of Leo the Lion. I will toggle the solar system objects on and off, so you can better see what I am talking about. This happens because Regulus is very close to the ecliptic, the daily path of the Sun. I have chosen Regulus in this video because you can see it very clearly. You can pick any star you like. The Sun and Regulus are in the same line of sight. For this video, we simplify and assume that they are in conjunction. This means that the observer, the Sun, and Regulus are currently perfectly aligned. Suppose it is now 12 o'clock noon. We start the clock and see what happens. We see the stars move across the celestial sphere from east to west, rising and setting. The next day, around noon, the observer has returned to being aligned with Regulus during transit, but we notice the Sun is lagging behind. We now check the time and notice it is just a few minutes short of 12 o'clock. It takes the Sun an additional 3 minutes and 56 seconds to get there. This means it takes the Sun exactly 24 hours to transit, and our reference star just under 24 hours. Why is that? We now know that the Earth rotates on its axis. This is what gives us our day-night cycle. This rotation period takes exactly 24 Earth time hours in respect to the Sun, that is, the time between two solar transits, as we witnessed in our experiment so far. But why did the Sun fall behind compared to Regulus in our transit experiment? The Earth rotates on its axis, but it also moves around the Sun. This movement actually causes us to place the Sun in a slightly different backdrop of stars each day. Imagine you are Earth, and your table would be the Sun. Circle the table while watching it closely, and notice the background view changes with each movement. This is what caused the separation between Regulus and the Sun. But how much did the Earth revolve around the Sun in our experiment? As this Wikipedia drawing shows, the angular distance by which the Earth advanced in orbit is the same to the angular separation between the Sun and Regulus we witnessed in our experiment. The two angles are marked in orange. Regulus is so far away that it virtually stays still. Now let's convert those 3 minutes and 56 second lag from time data to angular data based on the Earth's rotation. By the time the Sun returns to the meridian, the reference star will have an hour angle of 0.9856473 degrees, since 1 degree equals 4 time minutes. This is basically the angular distance Earth has put back on its orbit since the previous day. We note there are 365.242 days in our civil calendar. Multiply that by 0.9856473 and you get 360, which means that the Earth must fully go around the Sun in a tropical year, equinox to equinox. We have reached the final conclusion based on mathematical means. This, however, is not surprising. Even school children know that the Earth moves around the Sun once a year. But there is a problem. In order to explain the observable phenomena of precession, current lunisolar theory of precession assumes that the Earth goes around the Sun 359 degrees, 59 minutes and 10 arcseconds in a tropical year. The additional 50 arcseconds are attributed to a wobble of the Earth. Failure to comply to lunisolar rules would, in theory, result in a shifting of seasons in our calendar. Spring would eventually come on December 21st. This, however, has not happened. So which one is right? In order to patch things up, the International Earth Rotation and Reference System Service, the IERS, decided to change the rules of the game. They declared that the Sidereal Day, a term that since ancient Roman times defines the time interval between two successive transits of the same star, be changed. They redefined it as the hour angle of the vernal equinox, and confusingly renamed it to Stellar Day. Alas, virtually no one is aware of this. You can Google up Stellar Day and see how many websites you find. You can also search the IERS website. You won't find a thing. So dictionaries and astronomy books currently employ the same old terminology of Sidereal Day, but with different meanings attached to it. This leads to a general confusion, but in the process also resolves the great mathematical discrepancy which would have heralded in the demise of the lunisolar theory of precession.